Hello everyone. Today I'm going to deep dive into AutoEncoders, including architecture, training and sampling details, and underlying math. While doing that, I will also cover CNN basics and the close relationship between diffusion and AutoEncoders. I consider this episode to be one of the most important episodes of Gen AI image model series, since basic knowledge is covered and many concepts are used in later ones. Let's dive into it. In this talk, we will be going through basic concepts in computer vision, including convolution, pooling, upsampling, interpolation, and transpose convolution, and more. We will also go through details of autoencoders and VAE, including the architecture, the underlying math, the training and sampling details, and more. Note that diffusion is similar with VAE, so consider this as a prequel of diffusion. Let's do a quick recap on AutoEncoder. This is the architecture of AutoEncoder. It has encoder, bottleneck, and also decoder. In the bottleneck, the data is encoded in the latent space. So encoder will compress the original image to a lower dimension latent space. The latent dimension is supposed to capture the essential features of original image. And decoder will reconstruct the original image from the lower dimension latent space that's supposed to capture all the essential features. So how is it done exactly? Let's first dive deep into the encoder. So this is a very typical encoder architecture from online. As you can see, the original image is this dimension, and after a few layers, it became a lot smaller. And depending on the task that you're supposed to be doing, for example, if you're trying to classify this image to several labels, then your outcome could be very, very small. In our case, we want the autoencoders to compress to encode this image to a latent space. In this graph, we can see there are convolution, there are ReLU, there are max pooling, they are fully connected. So let's go through those terminology one by one. First of all, convolution layer is supposed to extract features from the image. For example, if it's an image of a bicycle, we should be able to extract wheels, we should be able to extract seat, and if there's a human on it, we should be able to extract the human and their body parts. ReLU is a activation function. It allows model to learn nonlinear complex relationship, and it helps vanishing gradients, and it's also very efficient computation-wise. The pooling layer is supposed to downsample features. It reduces spatial dimensions and computational complexity while retaining the important information. It also makes the model more robust to variations in feature position. The fully connected layer is flattening the input and map it to probability distribution as we need. So there are several concepts that I have gone through before in my transformer videos, for example, fully connected and the activation function. But in this video, we are going to go through each of the concepts in detail in the following slides. First of all, let's go through convolution. This is the intuition of what convolution layer is trying to do. For example, we have an image of handwriting 9. For a single image, we first try to identify simple micro patterns like straight lines and small curves. For example, the first layer is trying to capture the smallest patterns, small curves, straight line, etc. Then based on these patterns and its relationship with each other, we can identify more complex patterns like shapes. For example, circle, oval, squares, etc. In this case, we can detect circle pattern, vertical line pattern, diagonal line pattern. And based on these more complex patterns and shapes relationship with each other, we can identify even more complex shapes and patterns, like one layer after another. In the end, we should be able to detect very complex patterns, like human legs, wheels, eyes, nose, etc. And the shape identifiers should ideally be reusable. This is a follow-up example of how we capture those patterns. For example, for this handwriting 9, we put it in a matrix. We want to represent this 9 from a matrix representation. So if there are black ink within a box, we put it as 1. If there's no black ink, we put it as -1. This is the matrix representation of this handwriting 9. So now we have a filter that is able to detect loopy pattern. It's marked as green. This filter will be able to recognize a loop in this graph. And this vertical line filter is able to recognize vertical line in this graph. This diagonal line filter will be able to recognize diagonal line in this image. If we apply a loopy pattern detector to the matrix representation of this 9, we should be getting a 1 on top because there's a loop on top. And if it's applied to 6, the 1 should be down here because for 6, the loop is in this position. And for 8, we should have 2. For 96, we should have also 2. This is how we use a filter to detect a pattern from a mathematics and computation perspective. We use shape identifiers to identify patterns, and the shape identifiers are called filters or kernels. So now we have the intuition of what convolution is doing. And this is the actual convolution operation with the kernel. This is the kernel in blue square, and this is the actual image matrix representation. And after the convolution operations, we should be able to get a feature map from the actual image. So values in the kernel are all trainable parameters. We have the models to learn the parameters so we can extract features properly with those parameters. Convolution is to use the kernel to scan through the image and compute matrix sum product. And kernel values, that's learnable parameters of CNN, stay unchanged throughout the image scan. So the number of models parameter does not depend on the image size. It only depends on the size of the kernel itself and how many kernels are there. Now let's move to activation function. Activation functions allow neural networks to learn nonlinear relationship, and there are several kind of activation functions. There's sigmoid, there's tanh, there's ReLU, there's leaky ReLU, and there's maxout and ELU. I'm gonna go through sigmoid, tanh, ReLU, and leaky ReLU, which I think is more common. Sigmoid and tanh suffers from vanishing gradient problem, which means when the value is too big or too small, the gradient will become 0. You can pretty much get it from the shape. When the value is larger than this or smaller than this, the gradient is pretty much 0. It's very hard for the model to learn if the gradients become 0. ReLU improves vanishing gradient since the gradient is 1 for all positive values. The computation is also very efficient since the gradient is constant. It's 1 for positive and 0 for negative. However, ReLU can still suffer if the value of the model is constantly negative, causing 0 gradients. Then the model will stop learning, similar with the vanishing gradient problem. And the leaky ReLU is supposed to help on that. So the negative values still have non-zero positive gradient. It's just very, very small. For example, the positive gradient is 1 and the negative values gradient will be 0.1. If you're not sure what activation function to use, you can start with ReLU, leaky ReLU, or its variants. It won't go bad. Next, let's talk about pooling layer. This is an example of two pooling methods. One is called max pooling, the other is called average pooling. So pooling layer's purpose is to downsample the feature maps. It reduces spatial dimensions and computational complexity while retaining important information. It also makes the model more robust to variations in feature position. In this case, the convolved feature is 4x4, and for max pooling and average pooling, the kernel size is 2x2, and the stride is 2. It means every time we want to do pooling, we want to consider a 2x2 matrix. And stride of 2 means every time we will move vertically and horizontally by 2 positions. So in this case, after the pooling is done, the 4x4 matrix will be compressed to 2x2 matrix. And the difference for max pooling and average pooling is, for max pooling, we take the highest value within the kernel. And for average pooling, we get an average of all the values within the kernel. Max pooling is good at keeping the most apparent feature, and average pooling gets the average in a region, and it works pretty well for smoothing. They both have pros and cons. Average pooling, for example, it could miss out some details because it's trying to smooth everything. And max pooling is good at getting sharp details, but it also don't consider most of the other values within the kernel. We use the 2x2 pooling with stride of 2. It should reduce both length and width of the feature map by 50%. And there's no new parameters needed. We just need to get the maximum or average of the original feature map. And this is often added after the convolution layer. So now we have gone through the encoder part. How does decoder work then? In AutoEncoder, decoder's purpose is to reconstruct the original image from the lower dimension latent space. And based on the graph, it's almost symmetric. So a good guess is we just reverse the process of what encoder does, and it's pretty much correct. So encoder does convolution and downsample, decoder does convolution and upsample. Let's take a look. So how does decoder increase the image size? This is one possible method. We can use upsample and interpolation and then followed by convolution. So on the left hand side, this is the encoder operation that we have gone through. We have a pre-max pooling features and we have a pooling kernel which is 2 by 2 and the stride is also 2. In this case, the example is doing max pooling. So the max pooling feature map will be 45, which is the largest in this blue box, and then 96, which is the largest in this pink box, and then 65, which is the largest in this green box, and then 87. Other than keeping the max pooling features, let's also keep the pooling indices. So in this case, it's 0, 1, 2, 0, 1, 2, 3, 0, 1, and then 0. Now we have this two matrix. We can actually reverse the downsample and do the upsample. So now we have pooling features and pooling indices. Let's do an upsampling. Since it's max pooling and we already know the maximum value and the indices, so we can put the maximum values back to its original position, 45, 96, 87, and 65. And we can fill in the other values with zeros. The next thing we can do is interpolation. Interpolation is used to estimate or predict values between known data points. So the common way includes bilinear, polynomial, and I'm gonna give example of bilinear interpolation, basically using its closest 4 neighbors as average. So in this case, this 0, its 4 closest neighbor is 45, 0, out of edge, so it's 22. And let's take another example. This 0's for closest neighbor is 0, 0, 96, 87. We can use this bilinear interpolation and fill in all the values. So after upsampling and interpolation, usually followed by convolutions to learn how to rebuild simple and complex patterns with latent space features. This is a second example of transposed convolution. We have the pooling features, and in this case, for simplicity, I just put in 1, 2, 3, 4. Now let's say we have another kernel for transposed convolution. So it contains learnable parameters, and for simplicity, let's have everything as 1, but the middle one is -1. So we can do the same convolution process, but in this case, we want to increase the image dimension. So step 1, we multiply this value 1 with the kernel. So it's 1, 1, 1, 1 minus 1, 1, 1, 1. And step 2, we multiply 3 with this kernel and add the existing value in step 3 and step 4. So after 4 steps, after we scan through the whole image with the pooling features multiplied by the kernel, we have this output. And this output is higher dimension than pooling features. And with the learnable parameters in the kernel, we should be able to reconstruct the original image or reconstruct some patterns with the kernel. With the features map after encoding its pooling layer and a kernel with learnable parameters aiming to reconstruct image with latent space features, we can bring back the image to its original dimension. Now we have gone through the encoder and decoder architecture of AutoEncoder. Let's do a quick recap on how it's trained. During training, AutoEncoder's loss function is comparing pixel-wise difference between the output image and the original image. That's also where the auto in the name comes from. AutoEncoder is great in denoising image. This is an example that I gave in the overview. So in the training process, we have an original image 7. We add noise to this input image and we feed the corrupted input into AutoEncoder. We try to reconstruct the original image and we compare this output with the good quality 7. And after some training, this AutoEncoder model should be pretty good at denoising. And for inference, when we pass in a noisy 4, it should output a good quality 4. And now I want to also recap a little bit on diffusion. Diffusion's mechanism is also based on using model to predict noise for noisy image. So we have the capability to iteratively remove noises and generate good images. There are many overlap in architecture, underlying math, training, and sampling with AutoEncoder. So stay tuned on the diffusion deep dive. Next is from AutoEncoders to variational AutoEncoders. The goal of AutoEncoder is to reconstruct the original image. However, for a generative model, what we want is, given observed samples X from a distribution of interest, we want to learn to model the true data distribution Px. In plain words, we want to generate new samples that resemble the original input instead of just reconstruct the original image. That's why autoencoder is not good for generative tasks. There are other reasons, like autoencoder is fixed, it's deterministic mapping, and it's discrete on the latent space. And this is an example that I gave in the overview. Let's say this is a latent space of number classification task, and each dot in this latent space represent a observed examples mapping into the latent space. All the numbers here should be from 1, and all the numbers here should be from 0, and the middle part is very noisy. If we sample a random point from this 2D space and feed it to the decoder, it should be able to generate a new image that is similar to one of the 0 to 9 digits. If we sample a point here, it should generate a good 1. If we sample a point here, it should generate a good 0. If we sample a point in the middle, it's hard to tell. If we sample somewhere in very far, it's also very hard to tell. So that's why autoencoder is not perfect for generative tasks. It brings us to variational autoencoders. So instead of being deterministic and discrete, VAEs are probabilistic models. VAEs encode latent variables of training data not as a fixed discrete value z, but as a continuous range of possibilities expressed as a probability distribution. So it's represented by a mean and a standard deviation. So autoencoder mapped the original image to a discrete point, a fixed point, but variational autoencoder map it to a distribution instead. So instead of having a discrete points where there can be blank space, the latent space for VAE is continuous because it's all distribution here. Points from anywhere should theoretically generate a good image that's similar to some data in the training dataset. So this is the architecture of the variational autoencoder. It's very similar to autoencoder. The only difference is the latent space here. The latent space is represented by mean and variance, and we sample z from the latent space, and decoder uses this sampled z to generate image. This is conditional VAE. With VAE, we can sample a random point in the latent space and generate new images similar to training sets. However, we can't generate a new image on demand. Say we want to generate a specific number instead of a random one. With conditional VAE, we will be able to achieve this. And the way we do it is having an extra input, a one-hot vector representing the label, and input it to both encoder and decoder. In this case, we use a vector to represent from 0 to 9, and the fifth element should represent 4. So when we pass in 4 as one hot vector to the encoder and the decoder, after the model is trained, this one hot vector's information should be represented in the latent space. And when we do inference, we should be able to pass in number 4 as one hot vector and sample any point in this latent space. It will generate the number 4 here with a different style maybe. And even if we sample the same point in the latent space, but with different y vector, for example, if we put in 4, it will generate 4. If we put in 7, it will generate 7. So we gain some control of the VAE's generation. Now let's talk more details about the underlying math. And with the underlying math, you should also learn the details of the training and sampling procedure. So let's say we have the following assumptions. We have some observed data x, that is xi to xn, and we assume the data is generated from a latent variable z, that's zi from zn. Data is going to represent the parameters of the model. The goal here is to maximize the log likelihood of the observed data. What we actually want is to maximize the likelihood, but the log likelihood is equivalent because log function is monotonic, and using log is going to make the mathematics a lot easier, so it's for convenience sake. So in this case, we want to maximize the log likelihood of the observed data. It means we want the model to generate images as close as the observed data that we sampled. So given px integral representation, can we just calculate this directly? This is a very good question. However, this is computationally intractable. The prior distribution pz is often chosen to be a simple distribution. In this case, it's usually standard Gaussian. Prior distribution means without any sample, our assumption of the distribution. And we already mentioned we want the latent space to be standard normal distribution, which is the same as standard Gaussian. The probability of x given z is typically a very complex nonlinear function defined by model, which is neural network with parameters theta. So it's very complex to calculate it. It's not worth it. So what to do now? We can use ELBO, evidence lower bound. Let's take a look. So we introduce the approximate posterior q phi of z given x, then use Jensen's inequality to derive a lower bound. Phi represents the approximation function's parameter. So first, we transform the probability of x to an integral representation, and then we add the approximate posterior into the function, and then we apply Jensen's inequality. This will be the lower bound of original log likelihood, and this is the ELBO that we want. Now let's expand the right-hand side of the equation, which is this part. Since it's log, we can transform divide into deduction. So this is why log likelihood is making mathematics more convenient. And then we can rewrite the integrals in terms of expectations. We have this, and then we rewrite the possibility of x and z to the chained probability of z and then probability of x given z. Since this is log, we transform the multiplication to addition. Next, we are going to rearrange the orders a little bit to this, and the reason is the KL divergence. You probably heard of it from my previous videos. KL divergence is trying to measure the difference between two distributions. And in this case, we want to measure the difference between PX and QX. The KL divergence is defined as this. This looks very similar to our ELBO, right? We can rewrite the lower bound expression to ELBO. The first part is unchanged, but the second part is basically the KL diversion of the prior and the posterior. So then we have the intuition of the ELBO. The first part is reconstruction loss. It basically encourages the decoder p theta of x given z to reconstruct input x well from the latent representation z. We want the decoder to reconstruct the input x as close as possible. And the KL divergence loss is trying to encourage the approximate posterior to be close to the prior PZ, typically a standard normal distribution. Note that we only care about decoder parameters of theta because it's x given z, so it's only in decoder. And we only care about the encoder parameters of phi because it's probability of z given x. This only concerns encoder. So you can consider theta is the decoder parameters and phi is the encoder parameters. Now to be more practical, the reconstruction loss is typically computed by MSE between original and reconstructed image. For example, if f theta is the decoder function and g phi is the encoder function, this is the MSE. And practically, we usually assume the prior distribution P to be standard normal distribution. So the KL divergence loss will be this. The sigma here is the standard deviation and the mu here is the mean. Then we have the final loss function formula. The loss of VAE is the reconstruction loss plus the KL divergence loss. We have the loss function. Now we can use gradient descent to maximize ELBO, as always, with one last obstacle. Let's recap a little bit. We plan to use gradient descent to maximize ELBO. The parameters we are updating is decoder parameters of theta and encoder parameters of phi. So the problem is, although ELBO is a function of encoder parameter phi, it's not differentiable of phi, since z is randomly sampled from the latent space represented by mu and sigma. So now we have reparameterization trick to the rescue. The essence is to change how sampling is executed. Instead of randomly sampling directly from this distribution, let's introduce a random auxiliary variable epsilon from a distribution that is not parameters by phi, usually from a standard normal distribution, then pass it through the new g function to sample the q distribution. The reason we want to sample this epsilon from a distribution that is not parameters by phi is because when we do gradient, if this is not parameters by phi, we don't have to care about it. The gradient is just 0. Since epsilon is fixed and not dependent on phi, now ELBO is differentiable against phi. For example, the most typical g function should be mu plus epsilon and the standard deviation. Here is a pseudocode of the reparameterization. The reparameterized function takes mu and the variance which is basically the square of standard deviation. So we transform this log variance to standard deviation, and then we sample an epsilon from the standard deviation and return mu plus epsilon multiplied the standard deviation, which is our g function here. So the encoder network should be able to output mu and the log variance, and we pass those two variables to this reparameterize trick, so it output a point in the latent space. Then decoder network takes this reparameterized z as input and try to reconstruct the original image. And then we do loss calculation and backpropagation. This is a more visualized view of why we need reparameterization. In its original process, when we do backpropagation, we can't continue. The backpropagation cannot propagate to mu and sigma because z is randomly sampled. It's stochastic. We can't do any derivative on it. But after it's reparameterized, this z is no longer random, it's fixed. What's random is this epsilon, but epsilon is not a function of any parameters in the model. So when we do backpropagation, when we do gradients, we can ignore this line and the backpropagation will just flow normally to all the parameters. So now we are able to do gradient descent to find parameters that can maximize ELBO. Great, mission accomplished. So this is all the underlying math of VAE. This is all for today's talk. Hopefully it is helpful. And if you like my video, please subscribe, comment, and like. See you next time.